Hello, I'm Joe Hamaker, and in this video I'll be discussing space systems parametric cost estimating. First, a little bit about me. I'm the director of DoD and NASA programs at Gallaudet Federal. Formerly, I was cost director at NASA. I've got 40+ years of experience with cost estimating using parametrics and applying it to space systems. My email address is at the bottom of the chart if you'd like to contact me. There are a variety of methods used to estimate the cost of space systems. I've chosen to bin those into 3 categories on this chart. The first category is that of grassroots or bottoms-up or detailed engineering estimating. And in this approach, we estimate the labor and material for each detailed task or process step in the work breakdown structure. The second approach on this chart, I've called it the analogy or expert judgment approach. And in this approach, we estimate costs based on the past history of hopefully closely analogous systems. Now, we may still make some subjective adjustments to the estimated cost if there are minor differences between the analogous historical systems and the space system that we're estimating. The third approach is parametrics, and in parametrics we use a cost model which relates cost to physical and performance variables, and that'll be our focus. This parametric approach is our focus today. First, an overview of space systems parametric cost estimating. Parametrics uses statistical equations which relate cost drivers to cost, and these equations are called cost estimating relationships, or CERs. In CERs, cost is the dependent variable, and the cost drivers are the independent variables. Now, mass or weight is almost always a cost driver or independent variable in space systems CERs for a couple of reasons. First of all, mass is always known early on in the definition of any space system because it's a very important parameter, so it's there for use. And secondly, as it turns out, that a CER for space systems that uses mass only typically explains a good bit of the total variability in cost. The coefficient of determination, or R squared, is the statistic that's used to measure the amount of explanatory power of regression equations. And in using CERs with mass only usually can explain up to or more than 50% of the total variability. Now, 50% is not good enough for a CER that you want to use for estimating, but it's a good bit of the way. We can get the rest of the way in goodness of fit by adding additional variables. And we'd like to get up to typically 70, 75, 80% R squared. So by adding additional variables, we can generally do that. And here are some examples on this chart of variables that you often see in space system CERs. The power in watts, for example, the data rate in bits per second. The destination of the space system is usually a binary variable that can be shown to be statistically significant in lots of CERs for space systems, whether the mission is flying in Earth orbit or a planetary mission, with planetary missions being more expensive almost always. The design life of the space system, measured in months or years, is often a variable you see in space system CERs. The software of space systems is usually estimated with a separate CER or a separate set of CERs, which are based on software lines of code or slot count or function points. The heritage of the space systems is usually a pretty big driver, and this is a measure of the percent new design. Now, if you're building a space system that's based on hardware that's already flown in the past and it's all off the shelf, you might think that the percent new design might be near zero. But that's rarely the case, because even if you're using all off-the-shelf hardware, you still have to integrate that into a viable system. And so usually we see something like 20% of the 20% being the lowest percent new design that you'd probably use. On the other end of the scale for percent new design, you might use 100% if all the systems and subsystems are brand new and having to be designed from scratch. There are cases where you might even use more than 100%. If the technology readiness level, for example, of some of the systems you're using is not up to standard, then you might use a percent new design that's more than 100% to reflect that technology development work that has to be done. Level of redundancy is another parameter that's often worked into space system CERs. Is it single string redundancy? Is it dual redundancy, or somewhere between, or even more than dual redundancy? Space systems complexity is measured by considering lots of subsidiary factors such as parts count, whether or not it has complicated moving parts, what's the material makeup of the space system, and what is the temperature, operating temperature. And those are just some examples of ways to get at this concept of complexity. There are many other variables that are used in space system CERs, both technical and programmatic, but this is a list of some that you see quite often. Some of the advantages of the parametric cost estimating method are listed on this chart. First of all, parametric cost estimating is faster in execution than detailed methods. It requires less estimating resources to execute. It's very repeatable and more adaptable to computerization. The parametric approach does require good statistical relationships between the cost and the cost predictive variables. And attention is usually focused only on the true cost drivers in the space system, while the less important details can be ignored. Now, back on detailed engineering estimating, for example, you really can't ignore anything, because anything that you leave out in a detailed engineering estimate is going to be left out of the cost. But in parametrics, we have the luxury of only focusing on the parameters that we worked into our CERs to predict total cost. So this attention to the cost drivers, only the cost drivers, and coupled with its speed and low labor requirements for execution and computerization, frequently leads to the performance of parametric cost analysis earlier in the life cycle of the project, and with a degree of agility that's not very practical or even possible using more detailed approaches. In addition, we get lots of ancillary capability out of parametrics. We can do cost sensitivity studies, cost optimizations, trade studies. Those are all natural extensions of the parametric technique and made possible by the use of parametrics. The real work in space systems parametric cost estimating is detailed on this chart. Step one is to collect, organize, and normalize the database upon which the CERs and cost model is going to be based. Then we have to develop the CERs, usually using regression analysis or a similar approach. Coding the model into a user-friendly interface. This can be as simple as a spreadsheet, or it can be a dedicated standalone cost model. Validating that the cost model estimates cost accurately is an important step, so that the users can be confident in the model. And finally, after the initial model is developed, we have the task of maintaining the model and constantly updating it as new data becomes available, or we want to add new capabilities. So these 5 steps, depending on the complexity of your organization and the capability of the cost model that you're seeking to develop, can take many person years to develop a cost model. And after that, you have pre-planned product improvement, PQ-DI, to do to keep the cost model current. Now, within Galilrath, we have a suite of cost models called the SEER suite that our customers use to estimate the cost of space systems and other systems as well, but we'll stick to space here today. The first one is SEER-SIM, which is the software estimating model. SEER-H is a cost model that estimates systems hardware, including electronics. SEER for IT estimates information technology infrastructure. SEER for manufacturing estimates hardware manufacturing and assembly cost and lets you go directly from CAD to cost. SEER-SYS is a model that concentrates totally on systems engineering cost. Now in space systems, systems engineering cost can be a significant part of the total cost. It can be 15 or 20% of the cost of a space system. So SEER-SYS allows you to focus on that. And then finally, we have a dedicated model called SEER-Space, which estimates the satellite bus cost and the cost of instruments or payloads that are on the satellite, on the bus, and is dedicated to space projects. The value of this SEER suite is that the work to develop these models doesn't have to be done by your organization. These models exist, they're ready to go, they come with training and expert consultation if desired, and we do the PQ-DI. So in conclusion, a parametric cost model can be done with relatively less effort than detailed methods. It's less susceptible to I forgots. It can provide you with the capability to do cost sensitivities, optimizations, trade studies, cost and schedule risk analysis. And the SEER suite of parametric cost models provides these capabilities right out of the box without your organization having to do all the work to develop the models. But the models can be calibrated to your organization's cost performance. So the models can be tuned to reflect your cost productivity levels. Galilrath offers training and support to these models as well. So overall, parametric approaches such as our suite of SEER models can provide your organization with a credible, systematic, and repeatable cost estimating process. I'll repeat the chart here with my contact information on it. Be happy to talk to you about this set of models or this subject, so feel free to contact me. Thank you very much.